Hi everyone and welcome back. In this video, we're going to talk about vector databases. This type of databases got popular with the huge progress of large language models and generative AI. So in this video, I want to talk a little bit about the basic system design, about the search algorithms, different similarity metrics, and internals of the vector databases. They are different from the classic databases because they store the arrays of data, the vector representations of text or images or videos or pretty much anything. There are a lot of use cases for these databases, starting from using them as an index for some internal machine learning algorithms, ending with storing a large amount of data and use it as a huge database of embeddings and run semantic search on top of this database. So in this video, I want to talk about the basic system design, tell you how they are different from the classic databases, what kind of search algorithms are used, how do you define and measure the performance of those algorithms based on the similarity metrics, latency and throughput, and a lot of high-level basic knowledge of the vector database. So what is a vector database? Vector database store vectors. And vector is an array of numbers. So we are given an array of numbers, and then the purpose of the database is to find similar arrays inside the database and return them back to the client. Now, why do we need it? And the answer is because every single text or word or a picture or a video can be embedded or transformed to an array of numbers. And if we can store those array of numbers in the database and can look for the similar arrays of numbers, then we can find similar pictures, similar videos, similar text, etc. It's called a semantic search when you can find similar objects based on the object that you give to database. Now let's dive into a little bit of linear algebra. As you can see on this diagram, there is a vector representations of the specific words. On the left, top left, you can see words, for instance, dog, puppy, cat, houses. And every single word is run through the algorithm that embeds that word into a vector. In our case, you can see the representative vectors of the specific dimension. When you say dimension, it means number of elements in your vector. That is called a dimension. And then for a second, we'll try to reduce the dimension from 7 in our case to 2 dimension and draw it into the plane. And as you can see here, if we draw our words as a two-dimensional vectors, you will see that puppy and dog would be closer to each other, and dog and houses would be far away from each other, which means they are not similar. For this comparison of the vectors, we would need to apply a similarity algorithm, which there are multiple. We're going to talk about them later. So high level, you see that vectors are further from each other, which means that the words have different meaning. The same use case at the bottom, where you can see man, woman, king, and queen. And if we do the same procedure, we reduce the dimension from 7 to 2, draw them on the plane, we can see that man and woman closer to each other, which means if we have this data in the database and now we are looking for a word boy, then likely we're going to get the man and woman back because vector that represents the word boy would be located closer to a man than to a queen, for instance. And this is a simplified version on how we can represent specific words into 2D plane. But in reality, every single word that gets transformed into the embedding or a vector would have more than 2 dimensions because every single element in your array or a vector is a dimension. In our case, we can see the array of 7 elements, which means it's 7D dimension of the vector. So we can't really represent it on the plane, but we can still use the similarity algorithms to compute the distance between 2 vectors and learn whether they are close to each other or far. Now, as we learn how a single word can be embedded or transformed into a vector, you can think about that the same approach can be applied to a sentence of words, to a text. It can also be applied to a video or audio files or pretty much anything. What is important here is that for every single type of data, whether it's a word or a text or a video, that would be a separate embedding algorithm that likely would be part of the specific machine learning model, then would extract the features and create a representation of that object as a vector. If it would be a video, for instance, then we would likely first to transform it to a text representation, we would also store the parameters of the video, like resolution, perhaps different frames. Then we would store the specific words or keywords from the video. So we would extract different features based on the object that we want to embed as a vector. And once it's all done, we can store it in the database and then use it to search as similar objects based on the query or the request that we are given to a database. When you think about the use cases, it's mostly about the similarity search. For instance, Spotify has their own algorithm for searching embeddings. Then it's the same approach likely applied at Netflix for recommendations. There's one more, for instance, if you have a picture with multiple objects, you embed that picture and then you run it through a specific algorithm that would segment your vector and then look for specific segments on the picture. And then if you have a database with pre-trained objects like cats, dogs, chairs, then some of the segment from your picture would find the dog and the other segment would find the word cat. And then you can say that, hey, I have three objects on my picture. I have a cat, a dog, and a chair. So this way you use the vector database to find the objects that exist on the picture that you feed to the database. The high-level workflow would look like this. As you can see here in the middle, we have a vector database. On the right side, you can see that first, we take the external data source, we take some documents or data that we want to embed and store in our database. So we get those data sources, we get those files or videos or pictures, we run them through the encoder that creates or encodes those documents and creates embeddings. Then those embeddings are stored in the vector database. The database is responsible for maintaining an index of the dense vectors, as well as perform a similarity search. So once we have the data in the database, then first, the user sends a query, which in case it's a text would be a sentence or a question. Then the text gets encoded using the same algorithm as the external data was encoded, and then it gets passed to our vector database that does the similarity search based on the query, and then it finds the similar items. It's called approximate nearest neighbor algorithm that is used to find the similar items to our vector. And then as it finds the similar items, it returns them back to the user. They are returned in the form of the vectors. So the user would need to decode them on the client side so they represent the text or the image or whatever is stored in the vector database. Now let's talk about the algorithms and performance. So before we speak about the algorithms, how do we measure the performance? And the performance in our case measured based on three different metrics. It's recall or accuracy of our query, its throughput, and its latency. So the faster the query, likely the less efficient or accurate it's going to be. So there is a trade-off that we are making here. And in the following algorithms that we're going to talk about, I'll also touch base on how we can sacrifice the accuracy but increase the performance. The most popular and efficient algorithms on the vector databases for semantic search are centered about the dimension reduction and somehow optimizing the query and the data so we don't have to query all the embeddings in the database because we can have billions of them. And then to perform a near neighbor search, for instance, we would need to scan through all of them. And that's what we want to avoid. So we're going to talk about three main types of algorithms. The first one is going to be the vector compression that will be based on the dimension reduction. The second one is going to be based on the hashing. So we would use a hash table approach for the search. And the third one is going to be based on the graphs or trees. Let's start with the compression algorithms, and the first one is going to be randomization. So in this case, when we are given a n-size vector, as you can see on this diagram, we have multiple vectors of the n size, which means they have n dimensions. And let's say that vector represents 100 dimensions, which means it's a very, very accurate representation of whatever the original object was. And we want to reduce the dimension. So what we do, we create a randomized matrix of size m, and then we perform a dot product between the matrix that consists of n-size vectors and our dot product, which in result ends up to be an m-size matrix that maintain an n-size vectors. This way, we were given an n-size vectors, and then we ended up with m-size vectors. And we reduced the dimension to whatever number we wanted. And it's important to note that whatever the randomized matrix was used for the dot product, for embedding these n-size vectors, would need to be used for the query that comes to this database. So if we use this approach, we want to use the same values of the randomized matrix on the query. This way, we have the same changes on the vector, whether it's the original data or it's a query. The next approach is product quantization. And it's applied in a very similar format where we would reduce the dimension in a way, but we would apply a different mechanism to do so. So as you can see on this diagram, we get a vector on the left in green. And what we do, we take that vector and we split it into multiple segments. Let's say we have a vector of 100 dimensions, so we split it across 33 dimensions, 3 vectors of 33 dimensions. And then what we do is we compute the k-means of all those vectors, which means that we compute the mean value of each segment. And in the end, from 33 dimensions that every segment had, we now have only one value, which is a mean of all the values. This way now, we reduce our dimensions from 100 or 99 elements to only 3. And then we search our database for the codes for every single segment. So instead of using our 100 dimensions, we search for instance, in our case, 3 different codes in our database. And then as we find elements that have that code, we return them back to the client. High level, what the algorithm does is that it breaks down the vector into multiple segments, then compute k-means or the mean value of all the elements in that segment, and use it as a search data for the queries. The second family of algorithms is based on the hashing, and this specific one is called locality sensitive hashing. So as you can see on this diagram, it works with the hash functions. As we receive vectors, we first apply hash functions to those vectors, and then based on the hash value, we put them into specific buckets. High level, what it does is it clusters the data. It puts all the similar vectors into the same bucket, and then when we search for a specific vector, all we do, we just need to check the buckets that are closest to the query vector. And then as the query comes, all we need to do is just search for a specific set of buckets, not all the data, but the buckets that are closest to the query vector, and then return the result based on that. So we are not scanning all the data, we scan only the closest buckets. And the last algorithm is based on the graphs. And the way it works is that as we receive data, as we load data in our database, we first group data together. So we do the clustering algorithms on our data and create small clusters of vectors that have very big similarity. And then we take these clusters and we connect them with edges between them by creating a graph where the edge represents the similarity. This way, as the query vector comes in, we can use DFS, BFS search on our graph to find the closest node based on the similarity metric, and then use the BFS algorithm on the graph to expand the radius of the search to find more matches for our queries. As you can see, there are a lot of algorithms that can do a semantic search, and they all can be used to target a specific issue or specific requirements for the database. But the key here is to use multiple algorithms in the same database and use the one that fits the data most. So when we have a database, likely we're going to be storing multiple types of data, and we should use the appropriate algorithm for a specific type of data. For instance, some of them work better with the short dimension vectors. Some of them support long dimension vectors with the same speed. So based on the type of data, we will want to choose a specific algorithm for our database. Now, as you're familiar with the basics of the vector database, how it's implemented, what search algorithms are used, in the next video, we're going to talk about how we would take this knowledge and scale them to have a full-blown database that would be storing large amount of data. I hope you found this video useful and you learned something new today. Make sure you like and subscribe. If you want to learn more about the system design, check out my resources and my course, and I'll see you in the next video. Bye.